Hello everyone and welcome back to the course. In today's lesson, we are going to start dealing with a new type of function. Today's lesson is going to be about rational functions. A rational function is a function made of a division of two polynomials, p of x and q of x, where q of x is different than 0. Thus, if r of x is a rational function, then r of x is equal to p of x over q of x, where q of x is different than 0. For example, a rational function will be the function r of x equal x cubed minus 2x squared plus 3x minus 4 divided by x squared minus 2x plus 1. Now, there are some important concepts that we need to have in mind when working with rational functions. The first three are horizontal, vertical, and slant asymptote, and the last two are zeros and wholes of rational functions. Let us start defining what a zero of a rational function is. Let us suppose that we have a rational function r of x equal p of x divided by q of x. Now, if x null represents a zero of r of x, then x null must be a zero of p of x. Therefore, all of the zeros of r of x are the zeros from the polynomial in the numerator of that expression. For instance, if our rational function is r of x equal x squared minus 4 divided by x cubed, then the zeros of this rational function will be the zeros of the numerator of that expression, meaning the zeros of the expression given by the polynomial x squared minus 4. And the zeros of this polynomial are x equal 2 and x equal negative 2. Now, if we have a rational function r of x equal to p of x divided by q of x, and a represents a zero both for p of x and q of x, such that a has exactly the same multiplicity, let us say n, for both polynomials, then r of x can be written as x minus a to the power of n times another polynomial u of x divided by x minus a to the power of n times another polynomial v of x. Now, the expression x minus a to the power of n appears both in the numerator and denominator. Thus, it can be cancelled out. Thus, we can express r of x as u of x divided by v of x. But when we graph this function, it will have a little hole at the point x equal a. This little hole appears only when a zero appears both in the numerator and denominator of the rational function, and this root has exactly the same multiplicity for both polynomials. For instance, let us consider the polynomial 3x plus 1 times x minus 1 divided by x minus 1. Here, the root is x equal 1, both for the numerator and the denominator. Therefore, when we cancel out this expression, we will have that our rational function is actually the straight line 3x plus 1, but it will contain a little hole at x equal 1. Let us consider a rational function r of x equal to p of x divided by q of x, and let us suppose that a represents a zero for the denominator of that expression, but not for the numerator. Then r of a equal to p of a divided by q of a will not be defined, and graphically it will represent a vertical asymptote. For instance, let us consider the rational function given by f of x equal to 1 over x. Now, x equals 0 will not be defined for this function f of x, because f of 0 will be equal to 1 over 0, and that is not defined. But graphically, this will represent a vertical asymptote at x equal 0. Another example will be the rational function g of x equal to x squared minus 7x plus 10 divided by x minus 2 times x plus 2. Now, the polynomial x squared minus 7x plus 10 can be written as x minus 2 times x minus 5. So our rational function becomes x minus 2 times x minus 5 divided by x minus 2 times x plus 2. The expressions x minus 2 will cancel out. Thus, this polynomial will be written as x minus 5 divided by x plus 2. Thus, x equal negative 2 will represent a vertical asymptote for this rational function. The concepts of horizontal and slant asymptotes will be addressed in the next lesson when we study the concept of end behavior. In the meantime, try to solve the following problems. You are meant to find the zeros, the wholes, and the vertical asymptotes of those rational functions. And as always, see you in the next lesson.